So today's speaker is Jesus Rubio Jimenez. Jesus did his PhD at the University of Sussex under the supervision of Professor Jacob Dunningham. Jesus graduated in 2019 with a thesis titled Non-Asymptotic Quantum Metrology, Extracting Maximum Information from Limited Data. After his PhD, Jesus was a postdoc at the University of Exeter in the group of Janet Anders. And this month, Jesus has taken up a future fellowship at the University of Surrey. In a series of papers, Jesus has been bringing techniques from Bayesian estimation theory to quantum measurements. Jesus' research considers the realistic and important setting of quantum metrology without an infinite number of quantum states. And today we are very much looking forward to hearing. The virtual floor is yours.
Thank you very much, David, for the introduction. Allow me to start sharing my slides. Okay. So yes, thank you for inviting me. I'm very excited to be here today with all of you. And as David just said, I was previously at the University of Exeter, but I have just moved to Surrey. But obviously the results I'm going to present today were mostly done with my colleagues at Exeter. And what today I'm going to talk about is quantum metrology. So it's the idea of exploiting resources from quantum theory in order to improve how we perform measurements. But in particular, I'm going to introduce you to our latest development, which is what we are calling now scale metrology. And we will see in a minute what that means and how it's different. But it breaks apart from the usual framework of phase estimation that probably most of you are used to. So the way we're going to do this, you're very welcome to ask questions through, but just to give you an overview of what our plan is going to be for today, is the first two sections are going to be to introduce the basic notation and some of the ideas and the way I work with metrology, because there are different ways of doing metrology. And as David was saying, the one I have specialized in is the one in which you assume realistic resources. So you can have a finite amount of information, both a priori and also in terms of the data that you collect in the experiment. In fact, the most of this talk is going to be in a single shot framework. Now, after that, section 3 is where the new results are going to come, the metrology of scales. And the most exciting part for you probably is going to be how this can be applied to a series of different situations, including estimating the lifetime of an atomic state and also quantum thermometry. I will finish with how these results can be generalized to the multi-parameter regime, that within the community of quantum estimation theory, it's the part of this research area where most open questions are at the moment, and it's the most exciting one. So hopefully we will have time for a few comments there. So allow me first to give you a brief overview of what is the notion of precision that we want to use in quantum technologies. So of course, I'm referring to quantum technologies because even though I have specialized in quantum measurements as such, quantum metrology, this is having precise measurements is important all across the different technologies of the different quantum efforts, including computing, communication, sensing, etc. So something that we need in order to introduce Bayesian ideas later is that we need to distinguish well between 3 types of quantities that we can find in any experiment. One of them obviously is the measurand, which I'm denoting by X, the quantity that we record in our apparatus. And the other one is the parameter that we want to know, that I'm denoting as theta. So we are all acquainted with these 2 parameters, that type of quantities. But something we have found is that in order to generalize metrology to new applications, you need to take into account a 3rd type of quantity, which is what I'm calling Y. This vector of Y is this in the screen. And these parameters are known, so they don't play a role in the measurement or the part of estimation. However, they are usually useful in experiments to calibrate the experiment. That's their role. So tag along the rest of quantities I'm going to show, because that will be important later. So with these 3 quantities, let's first focus in the unknown parameter, theta. There are 2 pieces of information that we consider the initial information. One of them is going to be obviously the state of the system, which is what I'm denoting by rho of Y. So the state may depend on the calibration parameters, but it will certainly depend on the unknown parameter theta, okay? And the difference in notation, just to not confuse anyone, is that theta in capital is meant to represent the real true value of the parameter, and theta with this other letter is meant to represent a hypothesis about it, okay? Now, if I stop here, we could talk about both Bayesian and non-Bayesian estimation. But because I'm going to talk about Bayesian estimation, I need to introduce another piece of initial information, which is what we call the prior probability, okay? So the best way I find to think about the prior probability is to think that is an object that gives us information irrespective of the measurement scheme. So that's what the prior distribution represents. Now, once we have the way to initialize the problem, we are going to perform a measurement. And as we know, formally, we need to introduce the notion of positive operator value measures to quantify this. And as happened with the state, it may depend also on the calibration parameters y. Of course, in order to do measurements of theta, we need to be able to connect the actual quantity to be measured, x, and the quantity we want to find, which is theta, okay? So in order to make a connection between these two, we introduced what is called the likelihood function. And because we want to do quantum systems, this is simply given by the Born rule. So we don't need to worry about this. However, let me say, this is an important point when we are applying some of these ideas to experiments, as I will show you later, because sometimes if you're not working with a quantum system, you don't have this likelihood model and you need to come up with it. So that's a complication that is not always as trivial as I'm going to make it sound today. Okay, so what do we want to do with all of this that I have just introduced? There are two things we want to find. One of them is the optimal measurement that I have put before, the y of x. But then we're going to want to find what is called an estimator, meaning a map that takes us from the measurements that we are recording in our apparatus to a value for the unknown parameter, which in this case is theta. And once we have this function estimator, we need to know how good the estimator is, and that's where we need a notion of uncertainty. So this notion of uncertainty is the reason I'm calling this is a slide about precision, because this kind of idea is at the center of all the calculations I'm going to do later, okay? However, we need to make a distinction that is usually not done in the literature of non-Bayesian quantum metrology, but if you're doing Bayesian metrology, you need to distinguish between these two cases. So there are two things we can do with all these tools, okay? One of them is that we may have already built a setup and we may have already taken data and we want to analyze that data. If that's what we are doing, when we want to assess the uncertainty and we want to find the optimal estimator, we need to use an uncertainty quantifier that depends on which doesn't depend on the unknown parameter because it's unknown, but it needs to depend on the actual experimental record or the actual measurement record. So as you can see, here I'm doing an average over theta, a probability distribution that we don't have to concern about them right now. And what I'm doing the average over is the individual errors telling me how each value of my estimate is, how different it is from the hypothesis that I could have about the unknown parameter theta. But as you can see, this uncertainty does depend on the measurement. And that's what we use in an experimental context. But if the question that we have is not about data analysis, but about how we optimize the actual design of the experiment, meaning how we find the optimal POVM, the optimal state of the system, etc., we need to formulate the problem in a way that it doesn't depend on theta because we don't know it, but also it doesn't depend on the measurement because at the stage of optimization, we don't know the measurement outcome either. Okay, so for the remainder of this talk, for the most part, it's this second error, the one I'm going to focus on. And as I say, again, this kind of distinction blurs when you are doing non-Bayesian metrology. So that's why I'm being careful in the definitions. So having taken that, let me tell you a bit more explicitly.
Sorry to interrupt you, Jesus. There are two questions on this slide. So on the second line, we have someone who asks if you could, well, they're basically asking if rho subscript y of theta. So this is this is your prior guess of what the density matrix is?
No, it's the actual state.
So, okay. So they are asking, is it the true state or is it your prior guess?
So what you don't know is theta. Theta is unknown. That's the part that you don't know. That's what you have to guess. But the functional form of it is assumed to be known. So you know the transformation already.
Okay. And then in the last line, they say, why does the uncertainty not depend on capital theta?
Sorry, on capital. Right, because capital theta, so that's in one of the features of the Bayesian approach. So capital theta In the first uncertainty, it does depend on capital theta because X will depend on the actual capital theta. That's where this comes from. So in the first uncertainty, that dependency is implicit, but it depends in the sense, it depends on X, not on capital theta. In the equation, it doesn't appear. But in reality, if you go to the lab and you do the experiment, the X will depend on whichever the theta happened to be. But in the second one, it cannot depend on capital theta because the point is that we don't know capital theta, and instead we use this prior probability to represent the knowledge of it. So whatever we may know about theta is encoded in this probability, but nothing else, not the actual value. Does this make sense?
I think it does. Yeah, thank you.
Okay, shall I continue then?
Yeah, I see. We just have a comment here.
Yeah.
From Stefan de Bievre. He's asked, is there a difference between p theta given certain values and px given theta comma y? Or is this just a misprint?
No, it's difference. Thank you. That's a good question, which will come later in the slides. But basically, the p of x given theta and y is what is called the likelihood function, and that's meant to speak about the measurement process. The p of theta is what we call the posterior probability, which depends on p of x, but it also depends on the prior. So p of theta is a more complete object that has both the experimental information and the prior information merged together.
Okay, thank you.
Okay, great. Those are great questions, actually, because it's going to simplify in the next slides. So let me just, having introduced the basic notions, as we have just discussed, I want now to tell you what kind of optimization problem we need to formulate. So obviously, as I say, the first thing that we need to focus is how we construct the deviation function. So as I said before, what this tells us is a measure of the distance between the estimators that depend on the experimental outcome and our hypothesis for the value that theta could have. Now, in different contexts, this function is called differently. So in order to avoid confusion, let me tell you, so sometimes you may find it called cost function. In machine learning, you might find it called loss function instead. In more older metrology works, they might be called error function. They all respond to the same notion, but it's this idea of distance between two quantities. So once we have that and we calculate our error functional, and I'm calling error functional for a reason that you will see in a minute, here is where the probabilities are more explicitly discussed, written, so we can connect with the question from before. When you have the average over both theta and x, you get a joint probability for both theta and x at the same time, and inside this you have the prior and the likelihood function together. So whichever physics you are doing, which in our case is quantum, is a quantum system, the Born rule is inside there, but it's also connected with the prior information. Okay, so this is a functional essentially because in the sense that we are going to look at this object in the following way. We have said that the prior probability is going to be given. The state, the form of the state, except C theta, is also going to be given. So that's our initial information. So what we don't know in this expression is going to be the estimator, the P of M, and possibly the control parameters, the calibration parameters Y. For the purpose of the talk, you can assume that they are known, but if you don't know them, you could possibly optimize them too. But for now, we focus on the estimator and the P of M. So the question is, how do we find the estimator and the measurement scheme that give us the smallest possible problem? And that is what both of Bayesian estimation does. And they also tell us what is the main difference between Bayesian estimation and the other approaches in practice. If you're using non-Bayesian estimation, the kind of questions you're asking is about finding bounds and trying to approach those bounds. And it's typically because you cannot formulate optimization problems as neatly as this one. But in the case of Bayesian estimation, which is essentially the key idea is to do this average of a theta, that's where the Bayesian part is coming from, it allows us to have like a template in which every possible estimation problem can be formulated. And at this point, I haven't even talked about scales or phases or anything. This is completely general. So that's one of the strengths of this approach. Okay, any question so far? Okay.
I think, yeah, for now, it seems to be clear. Yeah, thanks.
Good. Yeah, I just wanted to introduce some notions, but let's go now to the more interesting part of this. So one of the key, we might call it results or ideas that I introduced in the latest research I have been doing is the idea that depending on the type of quantity that you want to estimate, you need to formulate your estimation problem and therefore your optimization problem differently. Okay, so this table that you are seeing here is one of the final results of the paper, but I'm putting it up front here because it's easier to see what the differences are. So if you go to any paper on quantum metrology in the last 30 years, most of them are formulated using what here I'm calling location parameters. Okay, so by location parameters, what I mean is that usually you assume that your theta can vary between minus infinity and infinity, and the type of error that you associate with this is the square error. It's basically what leads to variances. And we are all familiar with this, and this is the one that almost everyone uses in practice. Now, a closer look at this reveals that the key property of this kind of formulation, when you use square errors, is that it's translationally invariant. And that's the key idea. So that begs the question, what will happen if we have different parameters that can be in different ranges and have a different type of symmetry, okay? So you may ask, why is this important at all, okay? So let me explain to you why with the case of phase first. Imagine that what you want to estimate is something that we call is a phase, meaning that it's a circular parameter, and therefore it can be only between 0 and 2 pi, and it has circular symmetry, etc. Now, if you go to the literature of non-Bayesian estimation, people go and use location parameters anyway, location parameter formulation anyway. But if you go to the Bayesian version, you will see that people recommend to use something like a sign deviation function, which is what you can see here. And intuitively, all of us can see that if we are using something that has circular symmetry, if we want to measure something with circular symmetry, our errors and our estimators should also respect that symmetry. So the question is, that's a very abstract concept. So I like usually to put this example because it's much more intuitive. The question is, what will happen if you are estimating a phase and you insist in using the formulation of location parameters? So imagine that you have here the cycle, okay? And imagine that I have performed 2 measurements in which I have got one result that tells me that the phase is a little bit more of 0, and another one that tells me that the phase is a little bit less of 0. If you just look at the left-hand side of this drawing here, you will intuitively guess that the error of my estimate should be very small because both values are very close to 0. But if rather to acknowledge the circular symmetry, you go and insist in using the mean square error, then you will find that the cycle gets stretched into a single line, and 2 parameters that were very close suddenly are one on the stream on the other. And that makes a very large error at the end of the day. So that's one example of why one needs to be very careful in how you formulate estimation problems. And this is a key idea that is only now getting to be more widely recognized. Even though sign errors are very old, they were actually derived, I don't know if it was the first one, but certainly one of the first ones was Holebo. So this has been known for a while, but still you keep finding that most papers in modern quantum metrology use the mean square error. So this is an example of what can happen. And it was exactly this intuition what led me and my colleagues at Exeter to realize that in certain problems, when you don't have a location and you don't have a phase either, you cannot use neither of these formulations. And that's why scale estimation came into the picture. And that's what I want to focus on for most of this talk now. Now, we will say later in the applications that the motivation for this was originally thermometry, so the estimation of temperatures, but I'm going to present to you the general formalism first, because it doesn't necessarily have to be used in thermodynamics. It can be used in more contexts. So the first question that we want to ask is, what is a scale parameter? And there are 2 ways of defining this, okay? If you go to a book of statistics, a scale parameter is usually defined with respect to a specific likelihood function. And it tells you that it has to have this shape, and usually it's like an exponential function essentially, and that's a scale of some sort. But when I was doing this paper, I found that definition was very restrictive. So then I looked for something that didn't depend on probabilities or states. And what I found is the following. When you are defining your problem, I have said before that you have 3 types of quantities. You have the measurand, the parameter, and the other parameters, the calibration parameters. So if you are in a problem where either your calibration parameters or your measurand, you decide that those values are large or small with respect to theta, with respect to your unknown parameter, then the role that your unknown parameter is playing there is to be a scale. It's a scale in the problem in some sense, and it's obviously a positive and a strictly positive quantity. If that happens, what you observe in the equations is that suddenly your probabilities, your estimators, your states are written in terms of ratios between the parameters of the problem and your unknown parameter. So when that happens, we say that we are doing a scale estimation problem. And what I want to show you now is, first, I'm going to show you the formal consequences of this symmetry. And then I'm going to do the same thing I have done with the sign before. I'm going to show you what will happen if you insist on using the mean square error when you should be using something that is more suited for scale parameters. So that, just to give you a couple of examples of what a scale parameter is in practice, of course, if you're thinking about estimation of temperature in a thermal state, then temperature appears, that you have your state written as the ratio between energy and temperatures. So temperatures are giving you the scale of energies of your problem. Or if you're doing a problem such as perhaps a Poisson process, or as we will see later, spontaneous photo emission, then you're going to have some sort of temporal scale, and that also can be seen as a scale parameter. Now, I'm going to give you the final result of this, and then I will show you a discussion of how we got into it briefly, okay? But the final result is that the two pieces that we didn't know in our optimization problem, that if you remember, they were the prior. We need to know how to come up with the prior, because the state is given by the experiment, but the prior, we need to think about it, and the deviation function. So the prior is going to be simply the inverse of the parameter, which is what is called Jefferson's prior. We'll go into that later. And the scale, the deviation function for a scale has to have a logarithmic role, a logarithmic form. And that was one of the key results that we did in the PRL that we published a couple of years ago. So keep those in mind, and let's see how we arrive to that conclusion. If you have any question, this is a good moment for asking, by the way.
So the only question that appeared during the slide was, could you give any examples of scale parameters, which you then did second later? So it seems like we're all in the clear now. Thank you.
Great, fantastic. Okay, let's go on then. So this is where Alice and Bob are going to make a bit of an appearance. So first, I want to discuss the notion of maximum ignorance, okay? So obviously, when you have an experiment, and I have worked with experimentalists, they usually have ideas about what the parameters that they don't know should be. And that kind of information can be very nicely put into this prior distribution. But in the most general case, we are not going to have that information. So the question is, can we have something like what is the initial point, the initial starting point? And that's what the notion of maximum ignorance comes about. Now, what several authors, but in particular, I find James the most compelling and the most intuitive to understand, argue for is that you cannot just say maximum ignorance in general, because that's an ill-defined problem. If you intuitively will say maximum ignorance, you will just put a flat prior between minus infinity and infinity, and you cannot normalize that or anything. So that leads to problems if you define it like that. But what he said is that, and other authors too, they argue that it could be maximum ignorance with respect to some property that you know that your estimation problem is satisfying. So in our case, we have seen that we want to estimate the scales, and therefore, the property is that scale invariance should be respected in the same way that circular invariance should be respected in phase estimation, okay? I want to make that analogy because that's actually how we found this. So the question we want to ask that, if the only thing I know about my parameter is the range where it is and the fact that it's a scale parameter, what is the maximum amount of ignorance that I should represent with that state of information? So that's why I have invoked here to Alice and Bob. So imagine that Alice goes and says that she wants to estimate theta, and therefore she's going to come up with a prior probability for theta, okay? So far, so good. But now Bob is going to come also to estimate the same theta, and he's going to come with another prior distribution for that theta. And the thing is the following. Imagine, for the sake of example, that Alice happens to be an astrophysicist and Bob happens to be a condensed matter physicist. Alice and Bob are going to be thinking in very different scales. And even though they're going to be estimating the same parameter, there is going to be a multiplicative factor between how they're going to define those parameters in this problem. And that's what I mean by writing the transformation theta equal to gamma multiplied by theta. Gamma here is a strictly positive quantity that can have any value, simply representing the different scales that Alice and Bob have in mind. But of course, despite that, they are still estimating exactly the same quantity, and we are saying they are both equally ignorant because they are maximally ignorant about this parameter. What that means is that these two probability distributions must be exactly the same. I mean, well, the probability infinitesimally in an infinitesimal range, I mean, they have to be the same. And if you equate this and you substitute the theta with gamma theta, then you get a functional equation that can be solved. And in this case, happens to give you a unique solution, which is what you find, the prior distribution that you find in there. This is the prior distribution, which is usually called Jeffreys' prior because he was the first to find it. And theta maximum and theta minimum are meant to be the extremes of the range where theta could lie. That's what this is meant to represent. So the bottom line of this construction is that if you were to use any other probability distribution than this for your prior, you will be saying that you have some information other than the fact that your parameter is a scale. So it is in that sense that this is maximum ignorance about scale parameters. It means that I'm assuming nothing else. Okay. Any questions? This is a good point to break too. Otherwise, I want to continue. Okay. So once we have convinced ourselves that that's the right prior for scale parameters, that was already known. Okay, this is not new. But there was an issue that I have told you in this story of metrology that we need to be very careful of about how we define errors. And as far as we knew, and my colleagues in Exeter and myself, no one had thought about what kind of errors you should use when you're, for example, estimating something like a temperature. And in the few papers that were about Bayesian estimation for temperatures, they were still using the mean square error, but something didn't fit well. So then we came up with the following argument. We said, imagine again, Alice and Bob, okay? And now we can just, for the sake of example, think that they have got a bit annoyed at each other. So they're going to estimate different things, okay? So Alice now is going to estimate a location parameter. And as we have seen before, that means that it can take any possible value between minus infinity and infinity. For example, a free energy difference or a position, that sort of thing. Now, with that, we know what we have to do. Our maximum ignorant prior is just a flat prior, and our error is the mean square error. So you can go and do estimation with that. Now, Bob is going to continue doing a scale. And we have just found that for scale parameters, Jeffreys' prior is the one that represents maximum ignorance. But what is the error? That's what the missing point was in here. What we found is that actually it is possible to map the prior probability for a location parameter into the prior probability for a scale parameter, meaning by this that we can actually find the transformation from one to the other. So then we thought, well, if the maximum amount of ignorance that we can have in each of these problems can be mapped in such a way, and a maximum amount of ignorance in a sense is fundamental because there is no more ignorance to be had about either of these parameters, then perhaps we can use that same transformation to go from the mean square error that we know to whichever error we should be using in the case of scale parameters. And doing that is how we arrive to this logarithmic error that you can see here, in which is a sort of a distance again between my estimate theta tilde and my hypothesis theta, but now appearing in a way that is a scale invariant. That's the idea, okay? So up to this point, you may tell me, well, that's all very good, but this is incredibly formal, and why this should be an issue in practice, okay? Why cannot we actually just go and use mean square errors as we have done all the time for these parameters? So in the final act that we have with Alice and Bob today, I want to show you an example of what will happen if we insist on using the wrong type of error in the wrong type of situation. So for the sake of example, okay, imagine that we are back to wanting to estimate a scale, okay? Alice and Bob are both estimating the same parameter again. And we are being told that this scale, this theta, is going to be between 0.01 and 100 in some units, okay? And we are told that it's a scale, but we are not told anything else. So then Alice goes and say, well, I don't care about this new formalism. I'm just going to do the square error version. So she goes and uses a flat prior, use a mean square error, find the optimal estimator for that, and then get the answer that the answer is that the value is roughly 50. And of course, here I'm ignoring measurements, okay? This is just drawing a random value from the prior distribution. It's as simple as that. Okay, so obviously, if you have something linear, you get something in between the range, fine. But then if Bob goes and says, well, Bob is going to use the scale estimation framework, he's using the prior 1 over theta, he's using the logarithmic error. It turns out that the optimal estimator is a bit different. It's not just the average of the prior as happened before. It's something that now involves a sort of an exponentiation operation. And I get that the answer is 1, okay? So let's think for a moment about what this means. Obviously, in absolute terms, 50 is roughly in the middle of this range between 0.01 and 100. But 1 is in the middle in terms of order of magnitude, in the sense that if you think about this carefully for a minute, to the right-hand side of 1, we have 100, which is 2 orders of magnitudes more. And on the left-hand side of 1, we have 0.01, which is 2 orders of magnitude less. So in fact, it is the scale estimation framework, the one that is telling me what is the middle point from the point of view of a scale, not from the point of view of absolute values. So to me, this is the most clear example I have of why logarithmic error should be used for the type of parameters that are scales. Okay, hopefully that's more or less clear. So do you have any questions so far?
There's one question here, and the question, is it always clear whether or not I'm interested in a scale parameter or an absolute one?
As a rule of thumb, I would say that if your parameter is strictly positive, there is a pretty good chance you're going to want to look into the scale estimation version. I don't know any case where even though having a positive parameter, you may want to look into the absolute value necessarily. There may be, I'm not entirely sure, but that's what I would say.
Okay, thank you.
Okay, good. Okay, so this is all I had to say about the origin, motivation, and constraints that the scale estimation imposes. So now I would like to go back to this idea of optimizing an uncertainty with respect to the measurement scheme and the estimator. Now, that optimization, it's done in the paper that you can see here at the bottom of the slides. This is the one on quantum scale estimation. And if you're interested on the analytical details, I do recommend you have a look there, because it's one of the few papers that has a proper analytical version of something Bayesian, because Bayesian usually involves a lot of numerics, essentially. But allow me to just go into what is the solution of the problem for the sake of continuing with the talk. So after calculating that optimization problem, the final output, the final result, is a set of steps that if you follow them, you actually get the solution of the problem, okay? So the steps are as follows. It's like almost like an algorithm, right? You start with your initial information that we have already established here in this purple square box, that is the prior distribution and your state parameterized, your parameter dependent state. What you do is that you do an average of those states with respect to some logarithmic functions, okay? And you calculate the order 0 and 1 of this, for k equal to 0 and 1. With those two operators, then you go and formulate a Lyapunov equation with a known being called S of y here. And as you can see, the row y0 and the row y1, they are the ones coming from step 1. And something important I would say here is that unlike in the theory of non-Bayesian metrology, the one that depends on the efficient information, etc., here we don't have derivatives, we have integrals, which numerically makes things way simpler. So that's a strength, a practical strength of this. Okay, so we formulate this Lyapunov equation and we solve for S. Now, that S operator, that's the key of everything. Once we have it, we calculate the spectral decomposition of it. And that has everything we need to do, because the eigenstates of S give us the elements of the optimal POVM for the given state and the given prior that we have fed it to start with. And the spectrum of this S operator allow us to calculate the estimator, which in the case of a scale estimation, it happens to be the exponential of the spectrum. So you take the exponential of the spectrum, and then that gives you the function that should be your optimal estimator for this problem. And that solves everything. If we just follow these 5 steps, it's a constructive approach to find optimal measurements and estimators. We can solve any problem that is based on a scale estimation. Now, this is the main result. What follows from here is going to be applications and what kind of questions we can answer with this. But this is the novelty, and this is something that, as far as I'm aware, it cannot be done with non-Bayesian approaches in such a neat way, because you don't have this nice optimization problem that you have come up with the solution, etc. And of course, being Bayesian, it means that this formulation is single shot, but you could extend it, and actually I did it in the paper. You can extend it to multi-shot versions, and then you can always treat a small amount of data, a large amount of data, a lot of prior information, a small amount of prior information, covers all the cases. So it's completely general, and the only assumption made is that the parameter is a scale. Okay, so let me make a couple of remarks, and then we move on to see some plots and some interesting results with this. The first thing I will say let me go back to this S parameter, the S operator. This S operator is, as I say, is the key, having all the information we want from a quantum estimation point of view. I have not covered something else that we can do with this in the talk because I thought it was too much material, but in the paper, you will see that it also allows you to construct quantum observables for parameters that in the standard formulation of quantum mechanics, you wouldn't have a quantum observable for. So that's, I think it's a strength, because if you couple the fact that this Bayesian approach give you a systematic way to find the optimal strategy with the fact that you can then use the optimal strategy to calculate quantum observables, it makes a very neat approach to explore this direction and potential connections with the foundations of quantum mechanics. So I think that's a very nice potential line to get explored, but I won't talk about it today. The other two things I wanted to say is that obviously I'm thinking about a quantum problem here. So we care both about the POVM and the estimator. But in the case of, for example, thermometry, when we first formulated this, we did it entirely classically, meaning that we didn't, we fixed the POVM, so the POVM didn't make an appearance, but the optimator was still the same. So by this, I mean that this scale estimation framework is valid both for quantum cases and for classical cases. And that's an important strength too of this approach. Okay, so just
a question here, Jesus. So we have a question there asking if you could clarify what it means to have the estimator as a function of S.
So if you, okay, this is perhaps not the most transparent way of writing this, but basically if you introduce, S has a particular form that is given by the form that the spectrum of S has a particular form, which I explore in the paper. And when you introduce that inside this expression, it becomes something that depends only on the probabilities of the problem. And in that case, you will see that it's easier to see how the likelihood function enters and how the prior probability enters there. So that's in the sense in which this is a function of S. It's a formal expression just to indicate how you calculate the actual function, the actual map that you use in practice.
Okay, thanks.
Okay. But yeah, I do, for that question, for the person who asked that, I do actually suggest that have a look at the paper, because this is easier for this discussion, but it's not the most transparent way of writing it. So I think the one in the paper will be easier to understand. Okay, let me then show you some examples, okay? So I'm going to cover two cases. So imagine first that we have an atomic state, okay, a very textbook example, but it's very illustrative. And we have this state prepared in a superposition of ground and excited states as per usual. And now this atom undergoes a spontaneous photon emission. And when that happens, it turns out that if we want to calculate the dynamics of this state, then we have this form that I'm not going to enter into how you derive it. This is a basic problem in the open quantum systems. But the point here is that this is going to depend then on an exponential function when we have, on the one hand, the dynamical time, but then we have a lifetime that is scaling how we treat, how big and small we consider that the evolution has gone for, essentially. So with this setup, which is very standard, now we want to do quantum estimation. And then the question it is, if I say that I don't know the lifetime of this particular atom, then the atomic state, then can we make a measurement at time t to retrieve and estimate this parameter? That's the question we want to answer. So as you can see, this is a prime example of having a scale parameter. It appears as a ratio, as we said at the beginning, etc. So we can apply the formalism. So what I want to show you is what happens if we compare different types of measurements, okay? So of course, the most obvious thing in what I have just said to do will be to look at the atom and say, okay, if I register a photon, then it has happened. If I don't register a photon, it has not happened. As simple as that. It turns out that we can write down a specific POVM for that measurement, which looks complicated, but is simply representing, again, the intuitive idea of whether the photon is there or not. And we can calculate with that what is the error that this measurement will give us. with respect to a tau node, that what this is representing the fact that this specific measurement, which is not optimal, as we will see, only works in a specific calibration point. So it depends on you giving a rough idea of what you think the lifetime is, which is what I'm calling here tau node, and then you can apply it. So that, by the way, is why we may call this measurement local, in the sense that it depends on this specific initial seed. And that's something that does not happen in general with the Bayesian approach. So we will see that in a minute. But because this specific measurement that is the intuitive one, that's the one we want to analyze, depends on that, then I have plotted here the error in the y-axis, this is the logarithmic error, versus the possible values that we could give to this initial hint at what the lifetime is, okay? And that's what the blue line represents here. So there are several questions we want to ask about this. The first one is this measurement any good? To answer that question, we need to calculate what is the error that you will have if you were to perform no measurement at all and just draw a random value from the prior distribution, which is what I'm calling prior uncertainty. And this is the purple line. And as you can see, the answer is the measurement is useful because for all the range is always underneath the prior uncertainty, which means that we always learn something. But what is obviously true here too is that for small values of the lifetime, we will learn much more than for large values. So this begs the question, can we do better? So to answer that question, then we can use the framework of quantum scale metrology and calculate the optimal measurement and its error. And that's what it's being represented by the green line there. And as you can see, we do better everywhere. And for small values is very close to the optimum. So for small values, the physical measurement actually could be okay, but for larger values it's not. So this is an example of how Bayesian quantum metrology can inform in practice how good our measurements are and what could we do to improve them. Now, to be fair, okay, it's important also to see whether if you were to use a standard metrology, not the Bayesian one, you will get any improvement at all, because it could be that you always get improvement and therefore using the Bayesian approach is not needed. So to answer that question, I calculated too the measurement that could be optimal according to local quantum estimation theory. And this is what you will recognize this L as the symmetric logarithmic derivative for those of you who are familiar with it, etc. And what we find is that this measurement is actually better than the original measurement, in fact, considerably better. And not only that, but for values of when the evolution time and the lifetime are roughly the same, in fact, this measurement is optimal because it hits our limit, quantum limit calculated before with a scale estimation. However, even though it's a very fair, it has a very fair quality, it's still worse than the one that the Bayesian approach gives to you. So this shows that if you want to be sure that you're hitting the right quantum limit, then the Bayesian approach pays off. Okay, and just to mention briefly that this is just an example, but in the paper I put forward a change of inequalities where you can do this more generally, and you can ask, for example, for the first inequality whether you're using the optimal estimator or not, and for the second inequality whether you're using the optimal measurement or not. Okay, so that's a very academic example, but I would like to finish with something a bit more interesting that has to do with release recapture thermometry. So if you have any question about the previous example, this is a good moment to ask before I move on to another topic.
I think there are no questions at the moment, Jesus. So yeah, feel free to go on.
Great. So you hopefully get a feeling of the kind of things that we can do with the formalism, okay? We have seen, do we hit the fundamental quantum limit or not? If we don't hit it, can we find the optimal measurement that hit the limit or not, etc. But we want to actually also be able to use this in experiments. So to do this, my colleagues at Exeter and myself team up with the group of Giovanni Barontini in Birmingham they were doing an experiment to do release recapture thermometry. And basically, we applied scale estimation to their setup to see whether it can be optimized or not. And as we will see, the answer is in the positive. So very briefly, let me tell you what the setup does. What they have is that they have a trap in which they have an atomic trap, in which they have the atoms in the first step trap at T0. Then the trap is switched off and the atoms span ballistically away. And at a later point, they activate the trap again, and a number of atoms smaller than the initial number of atoms get recaptured. Okay, so doing this process many times, you get with the data that you get from this kind of experiment is that you get a numbers of atoms that have been recaptured and the times at which these atoms have been recaptured. And the question is, can we estimate the temperature that these atoms have? So in this paper here, in the one in PRX Quantum, we show that the statistics behind this experiment is a scale estimation problem, and that's why we can apply the methods I have discussed just with you. And just to say, in terms of nomenclature, when quantum scale estimation is applied to thermometry, we are calling it in the literature either Bayesian or global quantum thermometry. That's the just to give you a guide for the papers. But okay, what can we do with this? So having said that, the first thing we wanted to see is whether we could use Bayesian thermometry at all with the data that our colleagues in Birmingham had. So this plot that you are seeing here is actual experimental data. Okay, so what happens is that they can measure the mean number of atoms I have explained before versus the times at which the trap was switched on in each instance of the experiment. And with this, they can do a fit, and the fit they use just least squares as per usual, nothing revolutionary there. But then what we wanted to see first is that, okay, if we just take the same data and we do no optimization whatsoever, and we just run a Bayesian algorithm, do we get the right temperature or not? Because obviously we wouldn't want to do all this if the Bayesian approach doesn't work. And what we found, as you can see in these two particular examples, is that we have consistent error bars with each other, and the fit is also pretty good, both for the least square that is red, but also for the Bayesian one, in this case is blue. Okay, we wanted to be sure that this was not just a one-off thing, so we repeated the same idea with many different different estimates of this, and we studied the variability that these estimates had. And what we found is that if we just apply the Bayesian approach to the data without making optimization, so without making proper use of a scale estimation, I mean, then the variability we observe, the noise to signal, the noise to signal ratio is roughly the same in both cases. So you could be thinking, rightly so, what's the point if by applying Bayesian techniques you get exactly the same answer? But the beauty of this is what happens if, rather than just taking the data as the people were taking them for the least squares, we inform how you should be, at which times you should be switching the trap on and off. And that can be done with the type of optimization I have shown you before. So what we found doing that is that basically the problem is that least squares guides the experiment into taking switching the trap on and off at times that, one, doesn't take all the information that you could have into account, and two, it actually wastes resources because it makes them to switch the trap at times that have no information about temperature. While if you use the formalism of a scale metrology, you can guide the acquisition of data in such a way that you make sure that all your data that you're taking is as informative as it can be. So I won't go into too much detail of how that works. That's all in the PRX Quantum paper. But I would like to share with you a very illustrative way to see what is actually happening in practice. So what we went and did was to say, take the least squares that I have just showed you as it was, and calculate the noise to signal ratio again, this variability idea I have mentioned, and see how it changes as we accumulate more and more data, which is what the x-axis gives you, and that's what the k represents. The k represents how many runs we have done. So as you can see with the red line, it starts with a bump in this logarithmic scale, and then it settles for an asymptotic limit, okay? Incidentally, let me say that this asymptotic limit is not the Kramer-Rao bound, because this is a very non-optimal way of doing things, but there is an asymptotic limit nevertheless. So what we thought is like, okay, rather than just using the same data that went into this calculation, can we then design a way to take the data, making sure that each piece of data is as informative as possible, I said just before, and then we optimize that using the scale estimation approach. And what we found is that if we do that, then the yellow line is the answer to that question, First is underneath the other one, so it's more precise, but also the convergence is almost instantaneous, almost basically from 50 shots or so, or even less, you are already hitting the asymptotic regime of this shot. So if you compare numbers, what this is telling us is that by guiding the experiment with a scale metrology rather than just using the standard least squares, we can get twice as much precision with half of the measurement data. And the reason this matters is because in this specific setup, it is expensive to take data. So you want to make sure that you do a number of experiments that is as small as possible. That's where the real usefulness of these techniques can come into be. Okay, just a remark, just to be clear that we don't get confused. The previous slide I showed you is with real data. That's actual data from the lab. This one that I'm showing you here is a simulation. So the point of the paper was to say, this is what they are doing with the data right now, but if you were to do the things a bit differently, then this is the data this is the quality of the data you could get. So that was the point of the paper, just to make that clear. Okay, so with this, I'm reaching the end. I'm gonna give you a very quick overview of another topic, but if you have some questions about the thermometry part, this is the moment to ask.
I think it seems to be clear in the chat.
Clear?
Yeah.
Good. Great. Okay, so let me finish because I have only 6 minutes left. So I have given to you an overview of what we have been doing the last 2 to 3 years, and it has been very linked to quantum thermometry. But as you can see in the example of the atomic state, it is more general than that. But the type of questions that people is looking into right now, and where most of the open questions are, is in what we call multi-parameter estimation. Because in most experiments, you have more than one parameter to be estimated. Even in the atomic trap that I have shown you before from the experiment, they had more than one parameter, but we simplified the scheme. But ideally, we want to be able to do metrology in a simultaneous fashion. Okay, so here there is there are some results that have been done for the asymptotic theory. Most of them are gravitating around the holographic bound, which is a fantastic tool to answer questions about, for example, quantum incompatibility, etc. But for the reasons that we were saying at the beginning of this talk, you want to be sure that you can use these tools in a regime with limited data, with perhaps not too much prior information. There is a need to do a Bayesian version of multi-parameter quantum metrology. And that's something I have been also working in, and I'm working in right now. So I want to share with you 2 results of this. One is that, first of all, of course, we can now do multi-parameter estimation for both locations and scales. So for locations, which is the second result here, is basically a few years ago, Jacob Donninger and I found in the PRA below a bound for multi-parameter metrology in a Bayesian setup, which it has a form that somehow resembles the Hellstrom-Kramer bound, but it's also different because it includes prior information. That's the main difference. More recently, when I was doing this program of quantum scale estimation that I have discussed with you today, I also did in the same paper a multi-parameter version. And what I found, very interestingly, is that the structure of the bound for scales is exactly the same. The difference being that obviously the first term in both cases has to do with the prior information. So in one of them, you have a logarithmic function involved, like in the other don't. But the second part, when it's the actual information from the measurement, it has exactly the same form, which I found quite interesting, and I will look into that. So something to be said about this is that these bounds are not saturable, because if they don't take into account the incompatibility of the different S operators associated with different parameters, and that's where the interesting aspect of this problem comes into be, which is what other people are doing with the Holebo-Kramer bound, and they are finding very interesting results. So I would expect these to converge at some point. But just to give you just 10 days ago, exactly before this talk, there was by Jun Suzuki a paper on Bayesian multi-parameter estimation that goes and finds a bound that is in the same spirit that the 2 bounds I have shown you here. There is the same idea. So John called them generalized personic bounds, because Personic was the person who 50 years ago set a lot of the foundations of this direction. But he's referring to this kind of bounds. So he has found a way to make them tighter which could potentially answer questions about quantum compatibility. So as you can see, this is a very alive field at the moment. I mean, I'm talking about something that happened less than 10 days ago. So it's quite interesting, and there are many interesting questions being addressed at the moment. Okay, so with that, I would like to finish, and I will be very happy to take any other question that you may have. And thank you for your attention.
Thanks so much, Jesus. That was really nice. I really appreciate your intuitive little examples to guide us through that kind of niche and heavy estimation theory. That was really helpful. I can see I have 2 questions already in the chat that I think relate to the slide where you were showing the optimality of like you had like a optimal measurement and the physical measurement and the Fisher information measurement. Yeah,
Next
this
one.
slide.
Yeah.
So they're asking, so the first question, can you comment on what optimality means here? For example, if I would just naively pick a constant estimator to estimate the same value irrespectively of the measurement, I would get a 0 risk at that exact point. So any strategy would struggle to be better than this naive strategy if the true parameter happened to be what my guess was. So what does optimality mean in this plot?
So yeah, that's an excellent question. So this mean logarithmic error that I'm plotting here, if you allow me to go back at the beginning, it's so 1 second. It's this expression, or perhaps even this one is better. So it's this expression here, the one that is in the box. So optimality is with respect to this expression, okay? But if you remember, in this expression, I am fixing the prior and I am fixing the state. So it's optimal with respect to this quantifier of uncertainty and having fixed the prior and the state. So the example that he would put in about the estimator, in this case, it wouldn't go because it depends on the prior you have. If you just put, you cannot just put, so I don't know if I understood the example exactly, but I cannot see this quantity to go to 0 arbitrarily in any scenario, essentially, unless your prior happen to be very narrow.
Okay. Yes, I think the example is that say that you just ignore whatever prior you have and you say, whatever I do for the experiment, I'm going to guess that the parameter is 5. And then obviously you would do very badly in most scenarios, but in the scenario where you were lucky and actually the parameter was 5, that particular estimation technique is going to have 0 risk.
Yes. However, that's the trick. Because we are doing Bayesian, you don't know what if 5 happens to be the true one or not. So you are always doing an average over all the possible hypotheses you could have. So that cannot happen. So optimality is with respect to this error here. What this person was saying would work if you use the non-Bayesian risk, but that's not what we're doing.
Okay, that makes sense. Thanks. And then I think the second question is on the same slide as before with the optimality and so here someone is saying that your Fisher information guided measurement seems to reach the optimal risk or uncertainty at the true value of the parameter. Is this something that's general? Does this happen for every single scenario or just for this atomic case looked at in this example?
Well, I'm not entirely sure what's the meaning of the so you cannot know whether this is the true value or not. I don't know what the true value is in this problem because I am using the error that doesn't depend on it because it's the one that's average everything. So there is no a notion of true value in this. To have a notion of true value, I would have had to done a simulation with a true value and with measurement outcomes that depend on that true value. But this is not what we're doing here. So this is like a general statement of what could happen in general.
Okay, thanks for clarifying.
I think David is frozen.
Okay, so it's just David, it's not me. Good.
Yeah.
Wi-Fi is not always obvious here. I don't know why. Hotel
Did
Wi-Fi.
I cut out?
You did
I
catch
cut
that,
out?
David,
Yes, yes.
It's all the
I was going
casinos.
to ask a question actually. So this
Mhm.
this may result in a bit of a circular philosophy, but is there some way that you can use these sorts of estimation methods to find out, looking at experimental data, whether the Born rule itself is correct?
Oh, that's a very good question, actually. I the only way I could see something like that happening is if we have a parameterized Born rule. So if we somehow can capture the idea of the Born rule with a probability distribution that has unknown parameters, then yes, we could certainly test that. But if we don't have that, if it is not in terms of parameters, we will be talking about not estimation, but about tomography. And I think it's similar, but I haven't worked in tomography directly. So I think it will be potentially different. Yeah.
And the other question I had was with quantum modern NISQ quantum computers, as far as I understand, they simply repeat the measurement 8,092 times or something like that. Is there some your estimation techniques could be kind of incorporated into measurement aspects of a quantum computer so that you could make greater utility of them or have more accurate outputs?
Yes, absolutely. I mean, I don't know exactly in which way they use quantum measurements at the moment, but I would imagine. So what you could do is to guide what measurements should be done using estimation techniques. So that's what could potentially reduce the amount of measurements you need to do. How important that is, it kind of depends on the application, okay? There are applications where you can do as many measurements as you wish, and it doesn't really matter. The Bayesian approach still gives you the right answer, but you could potentially spare it. But I still think it's important to use it because the Bayesian approach works always, essentially. So you don't have to think about whether it's going to break down or not. That's the strength that it has. So yes, I think it could be used, and the way it would be used, I don't know the details, but I would imagine it to have like an extra step into the usual workflow of a quantum computing algorithm, in which the measurement will have some sort of feedback loop or something like that, in which you will introduce the quantifier of estimation theory to say this is how the measurement should be chosen at this point in your algorithm. That's what I would think.
And then my final question, you'll be pleased to hear, is about what used to be called the Mandelbrot effect. So these are freak events. So does if in an experimental scenario there just happened to be a sort of a collection of freak events, how would that alter your estimation? So you've got a Gaussian distribution. It's possible to get detection events at 3, 4, 5 sigma. Are your estimation techniques able to deal with that sort of scenario?
Oh yes, of course they can, because the whole point of using so it's not very evident in these slides. Sometimes I choose to explain this differently, but Bayes' theorem is inside all of this. Okay, inside optimization, Bayes' theorem is implicit. So because of that, Bayes' theorem always incorporates whichever information you have. It doesn't matter whether it is rare or if it is very common in the particular sample that you have, and it makes sure to put the right weight. So it's not going to cause any issue at all. It can be applied always, in fact. And you cannot have, the nice thing about this, and this is just because of having a prior, because the prior, I like to think it as almost like an initial condition in a way, something that regularizes your problem. Because what happens is that this kind of, what you're saying is marginally related to the fact that if you have these sort of events, sometimes you can get estimates that may break down, and they might give you answers that are either incorrect or out of range, or that they don't take into account the rareness of the events. That can happen, but that cannot happen in the Bayesian approach. Obviously, so the Bayesian approach is not a magic box. Okay, if your data is bad, the answer is going to be bad. But the Bayesian approach guarantees that whichever data you have, you want to make the most of it. So yes, you can apply it confidently in that case.
Excellent. Very interesting. Thanks for the talk.
Thank you for the question.
This was great, Jesus. Yeah, thank you very much. And I guess we'll keep in touch about potential future work. guess we have
Yes.
common.
We have a conversation happening soon at some point, so we will
Yeah.
be in touch for sure.
Okay, well, thanks again for agreeing to do this. This was great.
Thank you for inviting me. I was very excited to share these research.